a GB2, if you want a 2
Yeah,
gap,
yeah.
there are other hexagonals. So what's giving you the strong correlation? You started with graphene, which is not known for correlations. So
Yeah,
can you give me an ingredient that's allowing you to make this statement?
Yeah, no, so it would be something with the material that has that will make it strongly correlated. I would like to correct, no, not correct. I would like to add a thing with graphene. So graphene has zero density of states. So it's actually, it will not go ordered at the Dirac point. But if you actually look carefully, what Coulomb interactions does to the Dirac cone is that it renormalizes the Fermi velocity, and that normalization is pretty big. So Coulomb repulsion is actually rather strong in graphene. You can think of it because there's no density of state, so it's very hard to screen it. It might be hard to think of it as it's just a Hubbard U. It's more long range, but even if you take out the Hubbard U from good DFT and beyond calculations, it's bigger than the bandwidth even in graphene. So
you're saying all of these, with the exception of the first one, possibly are Hubbard U correlations.
No,
the first one.
Yeah, no. I'm not saying that. The one that we will look a little bit into. This one is very likely in the ground state MOT insulator at undoped. So this one would probably be the closest candidate to say, well, take the cuprates and put them on a hexagonal lattice. The other one would probably have to argue a lot about what the pairing symmetry. But it's saying if you get pairing that you think is beyond non-S wave and it's been singlet, these are very good candidates to be chiral topological superconductors. So there's a few ifs there, but yeah. All right, any more questions? Okay, so I've tried to give you a flavor that this might happen just from group theoretical reasons. Let's look at some other properties. I always said that this is a fully gapped state. You can see it very simply, but actually calculating the quasiparticle energy, it looks like this. So you have the band structure and then just the expectation value of delta, but delta is these two. So whenever this one has a node, this one does not have a node. So if you take the absolute value squared of this, there's no nodes, it's fully gapped. Unless you sit at this gamma point or you sit at one of the k points, but as long as this one is not zero at gamma or a k, so you're not having undoped graphene, say, or you're not having it, having something at gamma would be pathological anyways. This is a fully gapped superconductor. So whatever you know about topological insulators, this is a fully gapped superconductor, and we can calculate the edge state spectrum. So we take this was actually done on a honeycomb lattice. You take a honeycomb lattice, you make edges. Doesn't matter if they're zigzag or armature, it all looks the same. So the gray line here are the bulk states, so clearly it's a full gap. And then you have edge states. So the red ones are the ones that sit on the right side of the sample, and the left one sits on the left side of the sample. So there's two edge states here. So one would think that topological invariant should be 2. I haven't shown that, but that would be an implication here. So let's actually look at the topological invariant. This is a superconductor-based time reversal symmetry. So generally we like to find a Schoen number invariant. One way to calculate this is to look at the winding of a so-called fermion number. So you have a property, I don't want to go into this in detail, but just give you a flavor for it. So we have a number here, we call a fermion number, and you look at this formula just describes how this winds when you sum over the whole Brillouin zone. So you let K sweep out the whole Brillouin zone, and you see how much this vector sweeps out. So if this vector just sweeps out a little bit, this number is going to be 0. If it covers the whole sphere, it's going to be the number of times you covered that sphere, the unit sphere. And you can actually reason why the topological number is 2. Because in the bottom of the band, so you sit at the very bottom, then this one is going to dominate. So this M is going to point in the minus C direction. When you sit in the top of the band, this one is again dominating, so you point in the positive direction. So that means when you go from the bottom to the top of the band, you need to go from this vector to this vector. And if you just do this, you don't sweep out the whole unit sphere. The only way you sweep out the whole unit sphere if you also rotate in the xy plane. By rotating the xy plane is rotating among these right here. And then you can actually just look at the order parameter. And you see this order parameter once, twice, when you go from angle 0 to 2 pi. So, how to say, well, if you just take the real part, it once, twice, and you add a complex, you even wind twice in complex space. So by just looking at this order parameter, you can actually say, well, the d plus id weighs twice around the gamma point, so the topological number is going to be 2. You can calculate it and you will get 2. And that's fully consistent with having 2 edge states as we had here. So that was the d plus id spin singlet. Let's do the same thing for the spin triplet. Spin singlet triplet. I want to use strontium ruthenate as a possible candidate here. So let's just look a little bit into the structure. So on the right side here is a cuprate, and on the left side is strontium ruthenate. And see, they are very similar. It's very suggestive, this picture. So instead of having a copper, you have a ruthenium atom, you have some strontium instead of some lanthanum or barium. So it looks very similar to the lattice looks very similar to the cuprates. It has a slightly different Fermi surface. It has actually 3 quasi-2-dimensional Fermi surfaces. We talk about the alpha, the gamma, and beta band. It's not particularly important to what I want to say, but I just want to point that out. And it's a tetragonal symmetry. It's probably 2D, or at least quasi-2D. The bands, as you see, they don't disperse a lot in the z direction. There's been some discussion if there's more dispersion in the z direction or not. And it's not a very high TC, but it's a superconductor. So why are we so interested in it? Well, it's likely because it is this chiral p plus I. Maybe it's this chiral p plus IP state. So how do you reason that it's a p plus IB state? Well, there are several related strontium ruthenate compounds that are ferromagnetic. And if you have ferromagnetic fluctuations, that, well, maybe you should think that it's been triplet state. This is a very hand-waving argument. If you look a little bit more what experiments have been able to decipher, it turns out that TC decreases if you have non-magnetic impurities. It would point to not being S-wave. S-wave is stable against non-magnetic impurities. There is both some NMR night shift, there's spin polarized neutron scattering, and that points to spin triplet. There's squid measurements that shows that it should be odd parent in space. There's some Kerr effect that measure broken time reversal symmetry, also some muon spin relaxation that shows it's probably broken the time reversal symmetry. I'm not an expert in any of this, so I'm just sort of trying to summarize some of the experimental results. I should say they are also experimental results. It's not consistent with this picture, so that's why there's a question mark here. But if you believe these, you would say, well, it needs to be spin triplet, and it's not S-wave, so the best thing we can do is P, but it breaks time reversal, so it should be a P plus IP then maybe. And why should I come to that conclusion? Well, I know it's a square lattice, and if you force me to be P on a square lattice, I actually belong to an irreducible representation, is going to give me a P plus IP. And P plus IP breaks time reversal, so that would be consistent with this. So there's a lot of things here that seem to be consistent. It's a little bit dangerous when things become consistent, because maybe you jump to that conclusion without it being fully clear. But there's a lot of data that points to there might be this P plus IB superconductor. Okay, so let's quickly just look over the properties of the superconductor. So it's a spin triplet P plus IP. It has this mixed spin component, so the D vector actually looks like this DC component. It's again fully gapped. When you have just this DC component, the quasiparticle spectrum just looks like this, as we discussed before. Again, with the order parameter looks like this. It will always have a gap, because whenever this one has a node, this one does not have a node except the gamma point. Gamma point is not where the Fermi surface is going to be, so this is always finite. And we can calculate a Schur number using the same Skyrmion winding as we did before, exactly the same. Now, with the same reason, the only thing we have to do is look at how many times does this wind around gamma, and it winds one time around gamma. P plus IP has one. If you're expressing polar coordinates, it winds one time. So you have a topology number is 1, and if you actually calculate this, the edge states, you find one edge state per edge. So with that, I covered a little bit on topological, chiral superconductors. I talked about spin singlet D plus ID and spin triplet P plus IP. And I tried to convince you that they are not as rare as one would think. You just have to be in the right, have the right crystal symmetry and the right tendency to pair in a 2D irreducible representation. So for the spin singlet case, you should be on a hexagonal lattice or a tetragonal lattice. And for the square lattice case, you should just demand spin triplet superconductivity, and you will generally get this P plus IP state. They are fully gapped superconductors, so you can think about a lot of things you know about topological insulators. You can just translate to these superconductors because they're fully gapped. They have a finite Chern number that sets by the winding of delta. So it's really delta that winds in this case. It's not this inversion of band structure, but it's really is delta that gives you the topology of this order. And the number of chiral edge states are simply set by this Chern number. So the D plus ID has 2 states, and the P plus IP has 1 state. And it breaks time reversal symmetry because of these I factors, but it at least preserves some spin symmetry. So with that, I think I covered the second part. Are there any questions before we move on?
So when you go back to non-superconductors, you see this robust transport effect, condensed conductance, Chern insulators, quantum insulators. Is there something similar coming from these edge states?
Yes. So you cannot have quantized conductance because charge is not preserved in a superconductor. But what you have is you have quantized thermal conductance because the particle numbers are conserved. So you actually get a quantized thermal conductance in these samples.
Has this been measured?
I don't think so. But don't take my word for it. But the P plus IP, the Strontium-Ruthenite, and maybe I should add that, what's been a big problem in that field is that no one actually seen these chiral edge states. They don't seem to show up. And there's been a lot of ideas why they are not there, why there's not spontaneous currents. Maybe it's because it's not a P plus IP superconductor. That's one explanation. Another one is that the edge states might not go sort of linearly crossing band, maybe has some kind of wiggles and it doesn't give you a preserved current and so on and so forth. So there's no quantized thermal conductance mentioned.
Going back to the thermal conductance, when they do thermal conductivity, is the data consistent with it being fully gapped? Because thermal conductivity is considered, a beautiful measurement for seeing fully gapped or partially gapped or whatever. Louis Taillefer is one of the big ones. Do they see the full gap in thermal conductivity? Because if they don't see that, then it's not surprising that there are problems with other.
Yeah, I actually don't know.
Okay.
I think. Maybe, no, sorry, I shouldn't say it. Maybe I'm confusing with some other materials that they thought there were nodes and then there were no nodes. And there's also a discussion, maybe there are nodes in the C direction for Strontium. I think that,
controversy about fully gapped in terms of the thermal conductivity. Therefore, I'm a little...
So I think it looks like there's nodes, but maybe the node sits in the C direction, and then it gets a little bit more complicated if we need to add the third dimension.
Because you've been dealing with it purely as a
2D, yeah. I've scraped the 3D. In this symmetry class is not topological technically in 3 dimensions, so you really have to argue for a quasi 2D description to get topology. So that's, so they get some complications.
Damn that.
Yes, exactly. My point, exactly. Yes.
Sometimes before there were discussions about the time reversal symmetry breaking the agents of Z-wave superconductors. And they assume the splitting of the zero bias conductance T. But can you comment what is the present status of understanding of this?
Yes, I don't know if I know exactly the present status, but so this is a cuprate, which is a well-established D-wave superconductivity, but on the edges maybe you get an additional order. So this doesn't come because it's in a 2D irreducible representation, you get an additional order on the edge. And if that order, an additional order tends to come with this pi half rotation, so you get D plus ID, but it could also be D plus IS, so you take a D wave and you add an S wave. D plus IS is not topological actually, it's break time reversal symmetry, but it's not topological, and you can see it is like you don't get winding in the complex plane around gamma point. So why there might be likely to break time reversal symmetry is not clear if it's topological, and I don't think someone has settled if it's D plus ID or D plus IS. We had some work trying to say it's D plus IS based on the spectrum on small cuprate islands. So I think there's some indications, but I wouldn't put a big bet on it.
Okay, so I'm just looking at how can I visualize it, for example, through economic spectroscopy. So if I'm crossing a chiral superconductor on the edge, I would expect to see a peak inside the gap, right?
Yes.
And then either side, if I should see, for example, the usual D-wave. So is there any criteria at the environment, let's say the metal side? Do you need a strong spin-orbit coupling?
No, no, there's no spin-orbit coupling here.
Okay.
What I'm going to talk at the third part, we need spin-orbit coupling, or generally some disorder of magnetic moments. Yeah, there's no spin-orbit coupling needed for this. It's the only thing is this, that you end up in the right 2D reducible representation. Well, as I said, the surfaces of the cuprate islands, the question from the back there, is another alternative that maybe can get D plus ID. But the most generic thing is just essentially comes from group theory. And I would say rather simple, take your hexagonal lattice and assume D-wave superconductivity and you have the chiral state essentially.
But then you should see them along the nodal, anti-nodal directions, and they should disappear perhaps at the nodal.
So in the bulk, it's fully gap because...
Yeah, that's okay. I'm talking about the edge.
Yeah, so the edge state... Well, I guess this might change a little bit if this is calculated on a honeycomb lattice, but generically on a honeycomb lattice with just one active orbital per site, you have the edge, you see the bulk gap closes here, so it's a slightly doped, think slightly doped graphene, it's simplest to think that way. And the edge states, they cross zero not exactly where they gap is. It's some adjustment. So this point here is not fixed in, at k, it doesn't happen in a specific k, but somewhere you're going to have two states crossing the spectrum, exactly where in k space, it can be up to some microscopic details. So of course, if you just plot the density of states here, you just sum over all k values, you should see something. So it will be hard to say did I measure one or two states, but you should at least see something, right? So I have until 13:30, right? Yeah. Yes. Yeah, okay. So, I find it extremely tiring to just sit for 2 hours. So I suggest everyone just stand up for 15 seconds and stretch. So I get a break too. I can drink some water. That's good. Okay, I hope you all got a little bit more blood to your brains, so you don't fall asleep now before lunch. Yes, now you have to sit. But listen really carefully. No. Okay, so the last part I'm going to cover is what I call spinless superconductors, and these are the system we're going to find Majorana fermions. Because in the previous topological superconductors, there was no Majorana fermions. Okay, so what is this story about the spinless superconductors? Well, if you are spinless, if you really get rid of your spin index, then your Cooper pair is necessarily even in the spin index because the spin index isn't there. So then you have to be odd in spatial parity for it to be fermionic. So you're forced to be p-way. Unfortunately, there's no known intrinsic spinless superconductor. We don't just go about and get rid of spins in real materials. But thankfully, there is multiple proposals for how you engineer this spinless p+ip state, say from the last 10 years. And technically, the topological classes you end up with is if you are 1D spinless, you end up often in class BD1, sometimes in D, if you don't have time reversal symmetry, but generally you do. And if you're 2D, you get this p+ip state and then class D. And see, I'm a little bit sloppy. I call it p+ip even in the 1D case, but that would just be a K. And it wouldn't just be P and not p+ip, but please bear with me there. So these superconductors, if they are spinless and they are p+ip in 2D, they can be topological. They don't have to be. It depends actually a little bit on the microscopic details. But if they are topological, the boundary state will be Majorana fermions. So these Majorana fermions will be, if the system in 1D, will be localized at the endpoints of your 1D wire. If you're in 2D, they will actually be dispersive modes, so modes that run around your domain, the same thing as we found for the D state before, or they could also appear as localized zero energy vortex states. And these are vortex states that are forced to sit at zero energy. They are not like the Carole-Matricon degen states that sits in the vortex core but not at zero. So before I tell you how to do this, I'd actually talk a little bit about the Majorana, so we are on the same page there. So it all started with Schrödinger, right, in 1925, sorry. So the Schrödinger equation, fine. It's problematic because you treat space and time not the same way. You do a second derivative in space and just a first derivative in time. That's not very good in terms of relativity. So Dirac came up a few years later with his Dirac equation, which treats space and time in the same way, so relativistically correct. And the price he had to pay was that he had to introduce a 4-component vector here for the wave functions, instead of just having it as being a scalar in the Schrödinger equation. And generally, they are 4x4 complex matrices, the Dirac matrices here. This 4-component vector turns out to be quite handy because it first codes for spin 1/2. And it also codes for the particle and its antiparticle, the positron, or in condensed matter, we like to call it a hole, right? And importantly, the electron is not the same as a hole in the Dirac equation. So they represent the electron here with the C operator. The Majorana equation is trying to make this Dirac equation real, getting rid of all the complex numbers. And Ettore Majorana managed to do this in 1937 by finding 4x4 fully imaginary matrices. So the whole equation at the end of the day, sorry, it should be a 3 there, I see, ended up being a fully real equation. You have a fully real equation, you should have fully real solutions. If the solutions are fully real in this language of creation and annihilation operators, the particle needs to be the same as the antiparticle, because if you get the antiparticle, we take the dagger, which is a complex conjugation. So if you see it in this hand wave, the solution to the Majorana is its own antiparticle, and I code this with the gamma operator here. Note, this gamma is not the same as the gamma here matrix. This is a creation for a particle that is its own antiparticle, which, based on the Majorana equation, we call the Majorana fermion. Because this is still a fermionic equation. It's still a fermionic statistics, but it's a real particle. The fun thing comes if you think about it this way. Okay, so this is a fully real particle. The electron is a complex particle, right? You know, and you go from a real number to a complex number by doing this, to take A plus IB, or gamma 1 plus I gamma 2. And this is what you can do with Majoranas too. You take two Majoranas, you form this combination, you get one electron. So you can see the Majorana fermion, or you can see one electron as being composed of two Majorana fermions. And I'm going to give you a specific Hamiltonian where this all works out. But for now, just bear with me with this colloquial reasoning. Or if you flip it, you can say, well, then Majoranas really have an electron. So what we've done is we've gone and split the electron. Of course, that's not possible. It's a fundamental particle. But what has happened is that the wave function of the electron has split in two separate parts. And in principle, we can separate these two parts in space. So one sits here and one sits here, and we can act on them independently. So we've fractionalized excitations, effectively. So this is, I'm trying to actually, yeah, good. Here's a picture of this. So this is a solution. Actually, there's a vortex here in the middle in a topological superconductor. These two states here represent one electron. It's the eigenstate that gives one electron. Half the electron sits on the edge of the system, half sits in the vortex core. They both sit at zero energy. So here is, half the wave function here, half the wave function here. And we can talk about it in this Majorana language. So you can think of it as half an electron, but of course it's an emergent particle here. Again, we haven't created a fundamentally new particle. And as a consequence, it always have to appear in pairs. Whenever you have one Majorana, it needs to be another Majorana somewhere. We can't just have half electrons floating around. And this really applies for condensed matter systems. In high energy physics, you can have the single Majorana in principle, but not here. So what's so fun with them? Well, I think this half electron business is pretty fun by itself. What you can do with them is that you can braid them. And you can think about it very simply, saying, well, if I really have an electron and I split it in space, it's clearly a non-local property. We should be able to do something. More formally, you say it has non-abelian statistics. That means if you have one Majorana and you have another one, and you take one Majorana around the other one, you actually don't just pick up a phase. For fermions, you pick up -1, for bosons 0. But you pick up another little matrix. And this is what non-abelian statistics is. So the idea is that you should be able to use, you should be able to do particle braiding, and that you can use for a quantum gate operation. So you can do a quantum computer. But since the processes in this quantum computer is this braiding, it becomes very stable, very robust. Because no matter how you braided the particles, as long as the braid looks the same, you have the same operations. So this is known as robust or fault-tolerant quantum computation. So this is one reason why a lot of people are interested in this. Can we actually use it? Can we use these Majorana fermions for this? Okay, so there was a little bit back on what is this Majorana fermion. So let's now look a little bit more specifically, how do we actually get this in the superconductor? So we already talked about quasiparticles in superconductor, how they're part electron and part hole, and they actually mix spin up and spin down. So here's just a Weyl transformation we saw in the very beginning with the factors V and U. And if you notice, these factors V and U are 1/2 when you sit at zero energy. So when energy is 0, this factor drops out and it's just 1/2. So the quasiparticle in the superconductor is equal hole and equal electron at zero energy. Because U and V are the same, so you are the same, C dagger plus C. And if it's equal hole and equal electron, it's its own antiparticle, right? Because you get the antiparticle by taking the complex conjugation, so you satisfy this. And as I say, we did have to ignore spin here. If you look at this carefully, there's different spin index here. So bear with me a little bit. We're going to fix that. But if you ignore spin, E equal to 0 particles in superconductors will be Majorana fermions. Piece of cake. The problem is that, actually, let's come back to that figure later. The problem is that superconductors often have an energy gap, so you don't have these particles as E. 1 and sort of add it, and then you take -2, and then we'll say you have charge -1. So this is how superconductors get rid of charge for the quasiparticles. The charge doesn't matter because you can always take -1